Right, we'll take a look at the second part of section 3.1, and then we'll look at the first part of section 4.1. So we talked a little bit about inverse sine yesterday, and basically inverse sine is the opposite, or it undoes regular sine. All right. So if you had something like this, and let me do it in degrees. If I take the cosine of 60, I get 0.5. Now if I do the inverse cosine of 0.5, what will I get when I get enter? 60. So cosine and inverse cosine, they basically cancel each other out and bring you right back to what you started with. It's kind of like typing in something like this. If I do the square root of 5 squared, what will I get? What's the square root of 5 squared? 5, right? Square root and square. You've done two operations that cancel each other out, so it's like they're not even there. That's kind of what inverse sine and regular sine do. Right? So that's what I'm saying right here. Inverse sine and regular sine cancel each other out. Don't cross this out in your notes because it'll mess you up. You need to be able to read it. These things cross each other out, and all that you end up with for the final answer is what you originally started with. All right? But that only works between certain values, and we talked about some of these values yesterday. It only works if you plug in a number between negative 90 and 90. Or if you're thinking in radians, negative pi over 2 to pi over 2. And you can include the 90 and the negative 90. Okay, you can include them when you do the sine. You can't include them when you do the tan. So let's just pick a number between negative 90 and 90 and try that formula out. So Jake, give me an angle between negative 90 and 90 degrees.
45 degrees.
45 degrees. So I'm going to type in the inverse sine of the sine of 45. There is no multiplication in that problem at all. Okay, some people think when you have parentheses, it means multiplication. It does if you have a variable in parentheses or numbers in parentheses, like this. That means multiplication. That means multiplication. Here, that just means it's like a function, right? That's what that is. Sine is a function. It's not a variable. It's not a number. Sine is a word. Right? It's a function. So there's no multiplication here at all. It just means take the inverse sine of the sine of 45. Okay? That's what it means. So when I hit enter, what should I get according to that formula?
45.
Yep, I should get 45. Does anyone think I'm going to get something different? No? Let's try it. So we get 45. Right. Kayla, can you give me another angle between negative 90 and 90? 0. Okay. So if I type in the inverse sine of the sine of 0 and I hit enter, what am I going to get? 0. How come? Not sure. Can anybody tell me why am I going to get 0 there? Okay, because of the formula? Well, what if somebody said, how come? Why does that work? What's happening there?
Because the inverse sine and the sine will cancel each other out.
Yes, the inverse sine and the regular sine are canceling each other out, and you're getting back what you started with. Okay? Now, next time I'll try one not between negative 90 and 90, and I'll show you what happens.
Wouldn't it also work because 0, like anything times 0 is just 0, or is that like not apply here?
Well, remember, there's no multiplication there.
Oh, duh.
Right? This whole thing, there's no multiplication in that whole thing.
Right.
It's kind of like if you had the square root of 6. There's no multiplication in that at all. Even though you've got a square root symbol right next to a 6. Even if I put it in parentheses. Still no multiplication there, even though there's parentheses. All right. So let's try the inverse sine of the sine of 100. According to my formula, is that between the two numbers that I said it should be? No. So when I hit enter, I get an answer back, but it's not the answer that I started with, right? Because inverse sine will only give you an answer between negative 90 and 90. You typed in 100 to start. So it can't give you back 100 because that's not between the two numbers that it's always, that we said yesterday, right? So it's got to be between negative 90 and 90 for formula 2a to work. You don't have to know it's formula 2a, that's just what the book calls it, so I just use that name. Let's look at formula 2b. It's similar, but a little different. What's different between formula 2a and 2b? Still have two things canceling out and basically giving you back what you started with. Yeah?
You have the regular sign on the outside and then the inverse sign on the inside.
Yeah, you've switched kind of the order that you're doing the functions in. Again, there's still no multiplication here. All right? You're just taking the sine of the inverse sine of x. So if example 1 or formula 2a was kind of like doing something like this, this one is kind of like doing this. It's the same idea. You're still canceling out what you had. You're just switching the order you do the two things in. Here you're going to square it and then square root. Here you're going to square root and square. But the answer to both of these problems would just be what? 3. You just switch the order you did the operations in. All right. So this one only works if x is between negative 1 and positive 1. Now, where that negative 1 and positive 1 is coming from, it's coming from, has something to do with this graph. If you look at the graph, how high does it look like that graph ever goes? 1. It only goes up to 1. And how low? It goes to negative 1. Okay, the fact that the graph of sine is always between negative 1 and 1, that's where these numbers are coming from. All right. So let's try it. How about Aiden, give me a number between negative 1 and positive 1.
0.
0. So when I type it in the sine and the inverse sine cancel out, and I get back what I started with. All right. How about Connor? Can you give me another one?
No, 1.
1. All right, so he's going right on the edge. Negative 1 to 1. Plug it back in, and it cancels out. And get back what you started with. Right. Somebody give me a number that wouldn't work. Yeah. 3. Let's try 3. All right, by typing in 3, before I hit enter, if you want to kind of think about this problem visually, you're basically asking, when you ask me to type in 3, you're trying to make me find where that blue curve and red line cross. Where do they cross? They don't. So this time when you hit enter, you're not even going to get an answer because you're trying to do something that's impossible. So it gives you an error. All right. So in the first formula, if you type in a number outside negative 90 to 90, you'll still get an answer. But in this one, if you type outside negative 1 to 1, you won't even get an answer. Okay. All right. So let's look at really two different ways you could see a question like this on the test. So this example 1 says, is the inverse sine of the sine of pi over 8 equal to pi over 8? So I'm basically asking if those two things cancel out. All you have to do is check your angle and see if it's what it should be between. So example 1, is that one more like formula 2a or 2b?
2a.
Yeah, it's the 2a because the inverse is on the outside, the regular is on the inside. All right, so I'm supposed to be between negative 90 to 90 or negative pi over 2 to pi over 2. Well, this is giving me pi over 8. All right, so let's think about it from negative, think about it in terms of between negative pi over 2 and pi over 2. Here's 0. Here's negative pi over 2, positive pi over 2. We're looking at pi over 8. Where would that fit in on that number line? Yeah?
Would it be in the middle, like not in the exact middle, but like between 0 and pi over 2?
Right. Pi over 8 is smaller than pi over 2. Right? Think of 3 divided by 8. That's smaller than 3 divided by 2. So it might be somewhere right there. It's still positive, but the point is, it is between negative pi over 2 and pi over 2. So will that work if you were to type it in? Yes, it will. So the answer here is just yes. That would work. All right, let's try this one. Inverse sine of the sine of 3 pi over 2. All right, so we're supposed to be between negative pi over 2 and pi over 2, and we're looking at triple pi over 2. Yep?
No.
No. Right? Pi over 2 is the upper limit. So if you take pi over 2 and triple it, you're way past pi over 2. So the answer here is no. This is the one that if you typed it in, you would get a different answer back, but it wouldn't be the one you started with. Okay? If you wanted to think of it in degrees, that's 270 degrees. That's not between negative 90 and 90. Let's look at this one. Sine of the inverse sine of 1.5. Would that equal 1.5? All right, so now we're going to look at it. Inverse is on the inside. Inverse is on the inside. I'm supposed to be between negative 1 and 1. Devin, am I between negative 1 and 1 there?
No.
No, this is called your argument. So if you hear me say argument, all that argument means is it's the thing you plug into a function. So like if you wrote the square root of 2, you could say 2 is the argument. It's the thing you're taking the square root of. Well, 1.5 is the thing I'm taking the inverse sine of. But no, that wouldn't work. And let's check this one. Okay, same setup as the one above it. Regular on the outside, inverse on the inside. And my argument is 0.6. So if I typed all that in, would the calculator give me back 0.6? Yes, it would. Okay, so that's one way you could see a question like that on the test. The other way I could word it is I could say simplify, and I'll use the same problem we just did. The sine of the inverse sine of 0.6. I want to know what that would simplify to. If the question says simplify, don't write yes. Simplify means I want you to write a number for the answer. All right? The simplified is not a yes or no question. So what would be the answer there if you were to simplify that? 0.6, yes. Okay, but that always happens. I put a simplified question on the test and someone will write yes. No, doesn't work that way. Okay, so questions on that? Okay, so let's look at the same thing for inverse cosine. Okay, so we got two formulas here, and then we got two for tangent as well. Okay, inverse is on the outside, regular is on the inside. Those cancel each other out. Okay. Is there any multiplication in that formula that you're seeing?
No.
No, there's none. You're just taking the inverse cosine of the cosine. There's no multiplication. What did we have to be between yesterday when we talked about inverse cosine? Yep.
0 to 180.
We had to be 0 to 180. Yep. Which, if you're doing in radians, that's 0 to pi. And notice you can equal 0 and you can equal 180. Okay. So the B version of every formula today, that's when we put the inverse on the inside. Now, to explain what the restriction is on x here, last time I showed you a graph of sine, and I asked you how high and low it went. Well, I'm going to do the same thing. I'm going to graph cosine, and I'm going to ask you how high and low it goes. Okay, I'm going to leave sine on there. I'm just going to graph cosine on top of it in red. Okay, so here's sine. We already know that went 1 to -1. And here's cosine. How high and low does cosine go? It's the same. It's a little bit off. It's what we call a phase shift. The graph in red has been shifted to the left a little bit, or you could say the graph in blue has been shifted to the right. But they're basically the same graph, just shifted a little bit. But it's the same restriction, -1 to 1. Okay, so let's look at that one. So this is a yes or no. Is the cosine of the inverse cosine of 0.95 equal to 0.95? So Aaron, which formula is that one? 4a or 4b?
4b.
Yep, definitely 4b. I'm supposed to be between what and what?
I got 1, 1, so yes.
And the answer here, yes, I am. 0.95 is, it's getting close to that upper limit, but it's still not over it. Okay. And let's just do one the other way. Is the inverse cosine of the cosine of 210 equal to 210? No. What's the highest I can go? I can only go to 180. So if I type that in, I'll get an answer, but it's not going to give me 210. So no, it's not equal. Any questions on that one? Okay, and let's look at tangent. Okay, so formula 6a, inverse tangent of the tangent. It's like the square of the square root. They cancel each other out. But just like everything else, x has to be between two numbers. What did we say yesterday for inverse tangent? We got to be a little careful with this one.
-90.
So -90 to 90.
But they can't equal.
But it can't equal -90 or 90. That's why there's no equal to's. Or you could say x has to be between -pi/2 and pi/2, if you want to look at it in radians. Okay, formula 6b. Now we've got the inverse tangent on the inside. Okay. So the last two problems, how did I explain where the restriction came from? What did I do?
You mean like you showed the graph?
I showed the graph, and then what did we look at on the graph? Yeah, so we looked at the height, right? How high and low it went. Well, let's look at tangent. We'll do the same thing. I'm going to leave the other graphs up there. So I'll graph tangent, graph that one in pink. How high and low does it look like tangent is going? It does. It goes on forever. If you think it stops at 4, I could zoom out more and then you would see it does go above 4. It's just that's as high as my graph goes that you can see. But it does go up and down forever, which means this formula always works. There is no restriction on x. X can be anything.
Is that an infinity sign?
That's infinity, yeah. Should look a little more like that, but yeah. Okay, so another way you could say that here is x is all real numbers. There is no restriction. So, last one for this type. Is the tangent of the inverse tangent of 30.4 going to equal 30.4? Yep, and how come? What am I supposed to be between for this one? Yeah, anything. Anytime the inverse is on the inside, you don't even need to think about it for tangent. It automatically works. So if I give you one that says simplify, it's going to be one that's doable. I wouldn't give you one that doesn't simplify. Okay. But if it's a yes or no, it could be one that works or it could be one that doesn't. And we did a little bit of both. Any questions on that? Okay, so that's the end of section 3.1. So last section we're going to look at this week is 4.1. So if you've done like SOHCAHTOA, opposite adjacent hypotenuse, that's what this section gets into. Once we learn the definitions, which we're going to look at today, I'll explain the connection between today and what you did last week with unit circle trig. And as I said, they're the same thing. All right, so first thing we'll look at is just a few kind of basic vocabulary words that we're going to end up using in this section. Right triangle comes up a lot. So right triangle is any triangle with a 90-degree angle. Now, when you draw a triangle that has a 90-degree angle, the longest side has a name, and so do the two shorter sides. They have the same name. What do you call the longest side in a right triangle? The hypotenuse, yep. And what do you call the two shorter sides? The legs. So there's a picture of what we just said. We've got the hypotenuse, that's the longest side, and then we've got the legs, those are the two shorter sides. Now, when we have a triangle, there's a rule about what all the angles have to add up to. Okay. What do all the angles have to add up to?
180.
They all have to add up to 180. How much is that angle worth that I just circled?
90.
90. So that means these two together have to add up to how much?
90.
They each have to add up to 90. So you've got two different angles adding up to 90. That means they have to be acute, right? Acute is any angle that's less than 90, but also more than 0. So we've talked about negative angles. When we talk about the unit circle, like just changes the direction of rotation. A negative 10-degree angle is not acute. Acute has to be between 0 and 90. Right? So when we start dealing with trig functions, we're going to be dealing with one of these two acute angles. We don't really deal with the 90 too much because every problem we do in this section has a 90. We need something that's unique to our problem, and that's one of these two angles. Okay, not the 90. Okay. When you have a right triangle, there's a theorem that we can use, Pythagorean Theorem. And what does this theorem involve? Does it involve the angles in a triangle, or does it involve the sides? Yep, it involves the sides. And what does it tell me about the sides? What does it tell? Like, how would you use it in a right triangle? You had to explain it to somebody, not just telling them the formula, but like explaining what it tells you to do. Yeah.
I know a relationship between the lengths of the sides.
All right, so it gives you a special relationship between the lengths of the sides. Can you tell me what that relationship is?
A squared plus b squared equals c squared.
Now, what do you mean?
So,
I'm not sure. Well, I am sure, but
I know.
like, what's an A? Because I don't have an A, B, or C in a diagram here, so I'm not sure what you mean.
The length of each of the legs squared, well, the sum of the length of each of the legs squared is the length of the hypotenuse squared.
Exactly. That's exactly what the Pythagorean Theorem is. It says if you take each leg and you take their length and you square them and add them up, it's equal to the length of the hypotenuse squared. If you want to call the two legs A and B and the hypotenuse C, that's what it would look like. But technically you could call the two legs X and Y and call the hypotenuse Z. Okay, so that's a special formula that gives you a relationship between the sides, but only in a right triangle. Doesn't work if you don't have a right angle, but this week we will. We are going to have problems in a couple weeks where we don't. Not yet. All right, so I've kind of been throwing around some of these terms like opposite, adjacent, hypotenuse. We defined what hypotenuse means. It's the side that's across from the 90. I showed you in that picture. It's always the longest side. But two other terms that are going to come up are opposite and adjacent. So we just need to kind of explain what those two mean. First of all, opposite and adjacent are what we call like a relative term. They're from a certain perspective. They're like the words left and right. Okay? Left and right change. If I face the wall this way, left is the door, right is the window for me. If now I face the door, left is the front board and right is the back wall. So they're from a certain perspective. Unlike the word up. For us, up doesn't matter which way you turn, as long as you're standing on your feet, up is the ceiling. Okay? It doesn't matter if you face the door, if you face the windows. Right? So that's more of an absolute term. Okay? Up is always the same way for all of us if you're standing on your feet. Okay? So let's look at opposite and adjacent. And we're going to look at it from the perspective of the angle in the lower right. Does anyone remember what that Greek letter is called? Circle with a line? Theta. Yep. So if they want you to view everything from a certain perspective, they will put theta in the triangle somewhere. They'll either put it in the lower right, or they'll put it up at the top for this one. Okay, but it's always going to be one of the acute angles. So opposite is the side that's furthest away. Okay. It's the side that, I don't think I can just pull that, no I can't. But it's the side that if you just got rid of that side, you'd still have an angle right there. Okay. This side doesn't have anything to do with this angle down there because it's opposite, it's farthest away. Versus adjacent. Adjacent means that it's right next to you. Right? Like if I stand here, the table is adjacent to me. It's right next to me. Right? Adjacent is the side that if you got rid of the bottom side, you would not have an angle there anymore. Alright, so as I was saying, adjacent is the side that's right next to the angle. And if you think, well, aren't there two sides next to the angle? One on the right of it, one down on the bottom of it? Yes, but one of those sides already has another name, and that's the hypotenuse. So adjacent is the side that's next to the angle, but it's not the hypotenuse. Okay, it's one of the legs. So if it's still kind of not clear, I'll just write it out in words. Opposite is the side in the triangle that doesn't connect to the angle at all. It does not form one of the sides of the angle. Adjacent is the side in the angle that does form the angle. If you got rid of the adjacent, you wouldn't have the angle you're talking about anymore. Just imagine getting rid of this bottom side. There's no angle where I circled theta anymore. It just lost one of its sides. And again, I already explained that opposite and adjacent, those are relative terms. They're from the perspective of an angle. So if your perspective was there, that's opposite, that's adjacent. If I take the same triangle and pretend like you're walking to another spot, let's say you're standing up here, well, now you're looking at everything from a different perspective. Opposite is the side that's furthest away. Adjacent is the side that's next to it. And usually in a problem, you'll know kind of what perspective to look at it from because they'll give you one of these angles as an actual number. Whatever angle they give you, that's the one you use. So any questions on what opposite and adjacent mean? Okay. So now we're going to define the 6 trig functions, just like we did last week. But now I'm not going to use a coordinate. That's what we had to do before. We found a coordinate and we used the x and y values. Now we're going to use the terms opposite and adjacent and hypotenuse. So what are the first 3 trig functions we always put in that left column? Yep.
Sine, cosine, and tangent.
Yep. Sine, cosine, and tangent. Okay, so sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent is opposite over adjacent. So basically, a trig function is a fraction of 2 lengths. That's what it is. It's a fraction of 2 lengths in a triangle. Okay, so those were the first 3 we did. What's the next 3 that we always put in the other column? And try, if you can, give them to me in the order that...
Cosecant, secant, and cotangent.
Yep. Cosecant, secant, cotangent. And now, what did we always do with what was on the left? To get what's on the right, we just flipped it. So I just abbreviated because I was running out of space. But cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. Now, I said that this is the same thing as unit circle trig. When we did unit circle trig, sine, if you remember, it was y, but we always had to divide by r, just most of the time r was 1, so it didn't matter. Cosine was x divided by r, and tangent was y over x. Now, let me draw a triangle and compare those to what we just wrote. Here's a triangle, x, y, and let's pretend that here's my circle. That hypotenuse in my triangle, that's my radius, r. All right, so sine was y over r. But now, using the terms I just explained, y is the side that's farthest away. What's the name of the side that's farthest away? Opposite. And the name of the side that's across from the 90?
Adjacent.
Hypotenuse. So y is the opposite. R is the hypotenuse. So sine is y over r, but that really means it's opposite over hypotenuse. That's what we just wrote down. Okay. Cosine, x over r. Well, x is right next to the angle. So what side is that? That's adjacent. So cosine is x over r from what we did last week, but that's really adjacent over hypotenuse. That's what I just wrote down for cosine. Right? In tangent, we put opposite over adjacent. Well, last week we learned it's y over x. Same thing. Y is opposite over x, which is adjacent. So unit circle trig and right triangle trig are the same thing. Just two ways of looking at it. All right. Now, there's a trick some people use to try to remember the sine, the cosine, and the tangent. Does anybody know the trick? It's like a word I kind of remember. Well, it's just kind of a trick to remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent's opposite over adjacent. It's like an acronym. You know that? All right. Well, I'll show you. Maybe you don't know it, or maybe you're just not quite sure. So sine is opposite over hypotenuse. So sine is opposite over hypotenuse. Is that? Yeah, Sokotoa. Have people heard of that?
I heard that
From
from SpongeBob.
SpongeBob?
Didn't you say it like 10 minutes ago?
I might have said it already. Yeah, I think I did. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Sokotoa. So it's a way to kind of remember the first three. If you weren't sure, that's okay. At least in the past, one year I asked, how do you remember what it is? And someone said Sacagawea, but Sacagawea doesn't help. Not with this. But Sokotoa, that'll help. All right, and then if you remember the first three, you just flip them to get the other three. Okay. So any questions on the 6 trig functions? All right, so let's try an example. So the questions here say to find all 6 trig functions of theta. It's kind of like what we did with unit circle trig. We're going to find the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. But before we even start the problem, we're missing something. What are we missing?
Hypotenuse.
We're missing the hypotenuse. So you could answer the questions that don't have hypotenuse in them, but when you get to one that has hypotenuse, which is the top 4, you can't do it. How can I get the hypotenuse if I have the other 2 legs? Yep.
Do the Pythagorean Theorem.
Yeah. So if we just call that C, can you set up the Pythagorean Theorem for me, Connor, with those numbers and letters?
That'd be 3 squared plus 4 squared equals C squared.
Yeah. 3 squared is 9. 4 squared is 16. 9 plus 16 gives me 25. So C is 5. Now you've got all the sides that you need. Right? I'll do the sine with you, and then I'll have you guys try the other 5. The definition of sine. How about Caitlin? What's the definition of sine?
Opposite over hypotenuse.
Yep, opposite over hypotenuse. What side is opposite theta in this one? Yep, and what's the hypotenuse? And that's it. 4 over 5. Now, this one worked out nice because the hypotenuse wasn't a square root. But if the hypotenuse came out to a square root, and you ended up with something like that, you do need to fix it. So it's like that. Okay? Again, that won't come up in this one, but same thing we did last week. Okay, so take a minute or two and see if you can get the other 5 trig functions. All right, so as we go through the trig functions, it's kind of important to know what you're writing. What you're not doing is telling me how big that angle is. That's not the goal of this problem. We're going to get into that more tomorrow. The goal for this problem is just to tell me a trig function of the angle. Now, knowing that the sine is 4/5, I can figure out how big this angle is. That is enough information to do it. But for today, that's not what we're doing. Okay, let's do the cosine. Kayla, what'd you get for cosine?
3/5.
Yep, that's perfect. 3/5. And William, what'd you get for tangent?
You can do 4/3.
Yep.
1 1/3.
Yeah, we'll always leave it as an improper fraction. You don't ever have to change it to a mixed number. All right, and now that we've got those three, Allie, what do I do with each one of those to get the 3 on the right? Just flip them. So 5/4, 5/3, 3/4. Any questions on that? All right. Okay, so the last thing we're going to look at involves a theorem with complementary angles. And it's called the Complementary Angle Theorem. But before we look at the theorem, I just want to make sure people remember what complementary angles are. Anyone remember what it means to have angles that are complementary? You usually study supplementary at the same time, and some people mix them up. Jose?
Are they like multiples of 90, like 45, 90, and then something else than 180?
It doesn't have to do with multiples, but one of the numbers you said there is important with complementary angles. So something you said is important. Yeah.
Is this going to be like easier angles that add up to 180?
All right, they do add up to something, but not 180. That would be supplementary. Yep.
They add up to 90.
Right, 2 angles that add up to 90 degrees. Now, I kind of, I already addressed this earlier, but when you have a right triangle, and you got a 90, 2 angles that I just numbered, 1 and 2, are always complementary. How come? Why do angles 1 and 2 have to be complementary? And if they're not, you don't have a triangle. Yep.
Because the angles in a triangle have to add up to 180.
Yep.
That,
So why do 1 and 2 have to be 90 though?
because no.
Yep.
Because you already have a 90-degree angle, so you need another sum of 90 degrees to make it 180.
Exactly. Yep. So we already have a 90, so the other 2 have to add up to 90, or you're not going to have 180. All right. So let's look at the last idea that's going to tie in with what I call the complementary angle theorem. It's the idea of cofunctions. So cofunctions are another way to pair up the 6 trig functions we've been studying. We've always paired them up like this. Sine with cosecant, cosine with secant, tangent with cotangent. What's the fancy name for when you flip something? Do you remember it begins with an R? It's reciprocal. These are called reciprocal functions, okay? The ones that go left to right. Well, another way we can pair them up is what are called cofunctions. All that cofunctions are is you pick a trig function and then you put the word co in front of it, and that's the cofunction. So if you had sine and you put the word co in front of the word sine, you get cosine. If you had secant and you put the word co in front of it, you have co with the secant. It's called cosecant. And the last one they're cofunctions and reciprocal functions. They're the only ones that are both. Tangent, and then when you put the word co in front of it, you get cotangent. Right? So the cofunction for sine, cosine. Cofunction for secant, cosecant. Cofunction for tangent, cotangent. And it also works the other way. The cofunction for cosine is sine. You wouldn't say the cofunction for cosine is cocosine. That's kind of weird, all right? You don't put another co in front of a word that already has co, all right? Same thing here. The cofunction for cosecant isn't cosecant. It's just secant, all right? So those pairs are called cofunctions. So let's look at this diagram, and let's see how those two ideas connect, complementary angles and cofunctions. The diagram that I've drawn there, that's the standard diagram anytime you have a right triangle. We usually use A, B, and C for the sides, and we use Greek letters for the angles. The Greek letter that we put across from A is called alpha. The Greek letter we put across from B is called beta. Now, instead of using Greek letters, some textbooks use capital letters and lowercase letters, but that can start to get a little confusing. Because then if you said if you put like a C on paper, I can't really tell the difference between a capital C and a lowercase c unless it's in the context of other letters. Also, if you add a question, you say, I don't know how you got B. Well, if we used capital and lowercase letters, then I'd have to say, well, what do you mean? You mean like the capital B or the lowercase b? This way, if you say, I don't know how you got B, I know you mean a side. If you say, I don't know how you got beta, I know you mean an angle. Okay, so just kind of avoid some confusion. All right, so let's do some trig functions. Let's find the sine of alpha. Now, these aren't going to be numbers. They're just going to be a letter over a letter. Okay, so Kyle, what's the definition of sine?
The definition?
Yeah, what's the definition of it? Do you have it do you have it in your notes?
Yeah.
So we did it earlier. I wrote down all 6 trig functions and I said sine equals, and then I wrote a fraction of 2 things. And then I gave you like that trick that some people say Sacagawea to try to remember it, but it's not Sacagawea.
You mean like the opposite over hypotenuse?
Yeah, it's opposite over hypotenuse.
Oh, okay.
Yep.
Can I answer?
Yes, you can.
Okay, it's A over C. Sorry.
Yep. It's A over C. Now, I'm going to do 2 things. I'm going to do another problem, but I want to pick the cofunction of that. What's the cofunction of sine? Cosine. And I want to pick the angle that's complementary to alpha. So what angle in that picture is complementary with alpha? Beta, yes. So I did 2 things. I found the cofunction, and I found the angle that was complementary. And now I'm going to do that problem. Let's see what I get for an answer. So cosine. Jasmine, what's the definition of cosine?
Adjacent over hypotenuse.
Yes. From the perspective of beta, what side is adjacent to it?
A.
A, yep. Adjacent, over, and what side is the hypotenuse?
C.
C. What do you notice about the answers that I got to both of those problems? They're the same. Came out exactly the same. And that will always happen if you do the 2 things that I did. You first pick a cofunction, and then pick an angle that's complementary. Cofunctions, complementary angles. Okay? They always come out the same. And that's called the complementary angle theorem. It says that if you've got 2 cofunctions, and you've got 2 angles that are complementary, the answers come out the same. So let's look at each of these and see if we could figure out what that would be the same as using the theorem I just wrote. So you're going to do 2 things. First, pick the cofunction, and then find an angle that adds up to 90 with the one you were given. That's the complement. Sine. What's the cofunction? Ben?
Sine, cosine.
Cosine, yep. So we're going to have cosine. Now, what angle is complementary to 30? 60. Those two things come out exactly the same. The sine of 30 is the same as the cosine of 60. Cofunction, complement. Okay, let's do it again. Tangent of 15. What's the cofunction for tangent? Cotangent. And Peter, what's the complement to 15? What's the complement to 15 degrees?
30.
Well, do 15 and 30 add up to 90? So we're looking for an angle that adds up to 90 with 15. Not sure? Anyone help him out? What angle would add up to 90? 15 and 75. So cofunction, cotangent, complementary to 15, 75. Okay, let's try one more. Secant of 40. Anyone think I can tell me the whole thing, what that would equal? The cosecant of 50. Yep. Doesn't tell me, doesn't actually give me an answer. Like, it doesn't say, okay, so what is the secant of 40? Is it like 0.6 or what does it come out to? I still don't know that. But I do know something else that it comes out the same as. And you'll see how that is used right here. So I want to divide those two things, the sine of 15 and the cosine of 75. And they're both in degrees. What do you notice about sine and cosine? What's the name for those? They're what? They're cofunctions. 15 and 75. Those are complementary angles. We have cofunctions of complementary angles. Okay, so forget about that negative for now. It's in the front, but we'll come back to it. What does that mean about what's in the top and what's in the bottom? They're the same. I don't know what the sine of 15 is, and I don't know what the cosine of 75 is, but it doesn't matter what they are. I'm dividing two things that are the same, whatever they are. What happens when you divide two things that are the same? You get 1. And what happens if you put a negative in front of that? You get negative 1. Now, if you changed any one of those numbers, like if you made 15, 14, you couldn't do it. Not without a calculator. All right. So you had to have cofunctions, and you had to have angles that added to 90. All right, let's try this one. Tangent of 12 minus cotangent of 78. Jose, what do you notice about tangent, cotangent? What are those?
I just zoned out.
Well, what theorem, do you remember the theorem we're looking at? Sure. Aiden? Those are cofunctions, right? Tangent, cotangent. Those are cofunctions. What about, Jake, what about the 12 and the 78? Those are special angles. Do you remember it begins with a C?
Oh, the cotangent.
Well, we got that part. Tangent and cotangent are cofunctions.
Cosine.
But the 12 and the 78, because what do they add up to?
90.
They add up to 90. There's a special name for angles that add up to 90. Not supplementary, but
Complementary.
complementary. So we got cofunctions, and we've got complementary angles. So what does that mean about the two things I'm subtracting?
They're the same.
They're the same. I have no idea what the tangent of 12 is, and I have no idea what the cotangent of 78 is. All I know is I'm subtracting two things that are the same. So, what would I get?
When you just get 0.
What's that?
When you get 0.
Yeah. Zero. So this theorem kind of helps us to do problems if they work out special. Now, what about addition? Would it work if I add two numbers that are the same? Do you always get the same answer? No. If you add two things that are the same, you get that thing doubled. But it doesn't always come out to the same number. How about if you multiply two things that are the same? Do you get the same answer? No, you get that thing squared. So this trick doesn't really help you with addition or multiplication, just division and subtraction. Any questions on that theorem? All right, so first part of the homework, that's the yes or no questions we started out with on 187. So 46 to 51, 53 to 55, that's all. And then on page 255, that's getting into the opposite adjacent hypotenuse. And that's 9 to 21, just the odds. Okay, just odds. Okay, so reminder, if you have any tests to make up from last week, Thursday is the only day to do it after school. Otherwise, you're welcome to come any time of the day during school up until Friday. Okay.